Okay guys, so how is the assignment going? I have shared a lot of assignments in both modules. So this is the beginners module. This doesn't have much. So the actual module starts from module 2. So module 2 I have shared a couple of assignments, and again in module 3 also you have assignments. So how many of you have completed the two assignments in module 2, Python programming module? I hope everybody has completed these two. So please complete this guys, it's very easy. It will take just 10 minutes of your time. So watch the videos here and complete this. So Harsh, it wouldn't take much time. They are very simple problems. So try to just watch the videos and complete it. It will hardly take 10 to 15 minutes. Okay. And then we have the stats module. In the stats module also I have shared two assignments. Some of the assignments here are a little difficult. So you will have to watch all the videos and read the resources here. So these sections are not just videos, but some of them are I have taken a lot of information from some websites and I have put them here. Yes, it will be logged. So that's what is mentioned here. So do you see this? You see this? Modules and their sections must be completed in order. So only if you finish this module, you will have this module open. That is why there is a lock sign here. Okay, even for this. Only if you finish the assignments, you will complete this module, not without it. So I did this so that I want you to follow a structured approach, because only if you are comfortable in Python, you will follow in the stats part, and when you are comfortable in the stats part, you will be able to move ahead. But I think a lot of you are saying that this should not be there. Is that true, guys? Do you want it to be like that, or do you want me to remove such a requirement? So you want this to be there, or you want me to remove all the locks so that you can jump modules? Okay, so let it be there. I'll try to do something. I'll try to reduce the minimum requirement. See, because if I don't do that, I feel that a lot of you will skip the quizzes, and the quizzes are very important. Okay, so I want you guys to finish the quiz. I know it will be frustrating at times when you are not able to do, because some of the questions will be a little tricky. Amit, 2 or 3 times means, what does it mean? So right now I have given 50%. The requirement is 50%. Unfortunately, that feature is not there, Amit. I cannot do that even if I want to, because that feature, this learning management system does not allow that feature. That is the problem. I'll do one thing. Some of the quizzes which are difficult, I will reduce the minimum requirement. Okay. So instead of having it 50%, let me make it 30%. So this quiz is a difficult one. So instead of having it 50%, I'll make it 30%. So even 30% if you score, this quiz will be done. Okay. And you have the discussion forum here. I'm not sure if you guys have seen, because nothing has been posted here yet. So this is the discussion forum. I suggest you guys to go to this forum and then subscribe. Okay. So I will just add a link here. Okay, so you can use this discussion forum to discuss. So sometimes it becomes difficult to discuss in WhatsApp because you have to share links and all. So you can use this discussion forum. All you have to do is click on this post and write your question. Whatever questions you have, you may mention the headline of the question and then write your question. You can use all the links that you want. Okay, and people will be able to reply to that, so you can discuss. We can have a healthy discussion here on any doubts that you have. And I request everybody to subscribe to this, so that if anybody posts something here, you will get a notification that somebody has posted a question, and you can keep yourself updated. Okay, so click on this subscribe so that you will understand. Okay, I have subscribed, so a copy of each posting will be sent to your message inbox. Your message inbox is here. This is where you receive all your inboxes, so keep an eye on this notification button. You can click here and see basically. Okay, and all mails that I will be sending you will appear here. So all your mails will be appearing here. Okay, and I'll be sharing, so more modules will be created as our course proceeds. So today, for example, linear regression has 0 sections right now. So today we will cover linear regression, and even in the next 2 classes, we will take 3 classes to complete linear regression. And after that, more content will be added here. Okay, and I can see you guys when you are online also. So for example, Anupama is online right now. I'm not sure why she is not in the class, but she is right now online. So you can chat also if you want. So you can chat with other learners who are online. So you see this chat button, you can chat. Okay, and all updates that I want to give, I will sometimes post in the WhatsApp group, or it will also be mentioned here. So keep an eye on this section also. Whatever updates are there, I'll be sharing here. And this is where it is mentioned that you have to complete a module to unlock the next. Okay, so now let's jump to the today's course. So before we start to start today's topic, do you have any doubts from previous topics, guys? Do you have any questions from any of the topics discussed so far? So Arpita is asking, when do we apply binomial theorem and when do we apply norm.cdf? So Arpita, binomial theorem you apply when you are talking about a yes or a no problem. Okay, so whenever you are talking about a binary event, so a event which has a binary outcome, for example, tossing of a coin. Tossing of a coin can only give you a head or a tail. Okay, and one of so for example, if your question mentions find the probability of head, that means head is a success for you and all tails are failures for you. So this is a binomial outcome because you're talking about a success and a failure. Okay, there cannot be anything else. It is either a success or a failure. Similarly, when somebody is talking about rolling a dice and talking about getting a 6, let's say, that means getting a 6 is a success for you and all other numbers 1 to 5 are failures for you. So this is also a binomial event, though there are 6 outcomes, but you have categorized this as a binomial event because you are only talking about a 6 or not a 6. So this is also binomial in nature. So all such situations where your output is binomial in nature, you use a binomial theorem. Okay, and whenever it is mentioned in the question that it follows a normal distribution, that is where you use a normal distribution, norm.cdf. Okay, so for example, I think if you are talking from the quizzes, if you see the questions in this quiz, So here I have clearly mentioned here that it follows a normal distribution. Suppose the GMAT scores are normally distributed. That means it follows a normal distribution. So in this case, you will be using the norm.cdf function. Okay, is that clear now, Arpita? And this assignment, if you are finding it difficult, after you complete the assignment, you will have the solutions immediately. So I have discussed the solutions in details here. Okay, so here I have discussed the solutions in detail. So go through these explanations. Okay, these explanations I have worked very hard to get these explanations. Okay, so work on read these explanations well. Why is there a gap here? Okay. So today we will be talking about our first machine learning algorithm, which is linear regression. Okay. So if you remember, in the last class we discussed the different algorithms, the different uh, types of machine learning. So machine learning is broadly divided into two types, both of which we'll be covering today. One is called supervised learning. The other is unsupervised learning. Okay. So what is supervised learning? Supervised learning is that kind of machine learning where we try to find this function. So we have talked extensively about this even in the introduction video. So whenever there is a relationship like this where you have a dependent variable and you have some independent variables, okay, where you have a dependent variable and some independent variables and you try to find a relationship between them, this is called supervised learning. Why is this called supervised learning? Because the independent variables, they supervise the dependent variable or they influence the dependent variable. Okay, they decide the value of dependent variable and hence it is called supervised learning. Okay, and in these kind of supervised learning problems, our goal is to find this function f. Okay, what is the function f which gives us a relationship between the two? It can be a simple function, it can be a simple straight line, for example, or it can be a very complex polynomial function. It can take any shape. Okay, so this is our goal, that we have to find a function f which gives a relationship between our dependent variable and our independent variable. Okay, dependent variable is the variable of our interest. We have discussed this in the last class. So for example, the sales of a company will want to know what will be its sales in the future, let's say next year. What would be the sales of a company in next year, so that they can plan accordingly. A bank would want to know whether it should give loans to all the customers or not. So let's say in 2019 some 10,000 customers apply for a loan. The bank cannot give loan to all 10,000 customers, or the bank cannot manually evaluate, let's say, 20,000 applications. If 20,000 people apply for a loan, evaluating the application of all 20,000 people is very tedious, very time taking. So what the bank can do, the bank can develop models and they can rely on the models to evaluate the applications. They can just feed the data and allow the model to tell the bank whether they should give loans or not. Okay, so there also the bank will be finding this relation f. Okay, so how is this done? What is done is, see, in the historical data we will know both the dependent variable and the independent variable. So let's take the bank example. So for example, the bank has been, let's say, existing from 2010 onwards. So from 2010 till 2018 the bank will have all the data of all customers that it gave loan to. Okay, so it has the dependent variable. So the dependent variable here is 1 and 0. 1 means give a loan, 0 means don't give the loan. Okay, or 1 means customers who have paid their loans back, Zero means customers who have not paid their loans. This is on the historical data. So from 2010 till 2018, we already know the dependent variable as 1 or 0. 1 means customers who paid their loans back. 0 means customers who did not pay their loans back. Okay. And of course, we know the independent variables also. So independent variables are the variables which influence whether a person returned his loan or not, his or her loan or not. So what can these variables be? This can be several variables like income of the person. Of course, income of a person will decide whether a person returns his loan or not. It can be gender, for example. It can be the person's age. It can be the person's profession. It can be the number of dependents the person has. It can be the city in which the person stays. Okay. It can be the loan amount. How much loan amount did he take? It can be the tenure of loan. For how long did he take the loan? And so on. So these factors will decide whether the person returned loans or not. And remember this, I'm talking about the historical data here. So I already know whether these people or whoever the bank gave loans to in this period, in these 8 years, whether they returned or not. Okay. So this data is already known to me. So my Y, which is my dependent variable, this is known, and all my X1s, X2 and all these, this is also known to me. So left hand side is known, this is known. I can easily find the function f. Okay, not easily, rather it is a little difficult sometimes, but we can find the function f which gives a relationship between the two. Okay, now let's say I have found my function f. Now f is known to me. F is known to me. Now what I will do, come 2019. Now what I will do, now I know my f, and I will collect these independent variables from the new customers. Okay, from the new customers I'll ask their income, I'll ask their gender, I'll ask their age, I'll ask their profession, I'll ask the number of dependents they have, I'll ask the city in which he lives in, I will ask the loan amount, obviously I'll ask the tenure he is planning. So I will know all these details. What I do not know is whether he will pay or not. So y is not known to me in 2019, but I already know the function f. So I will just put all these variables in the function f, and automatically the function itself will give me 1 or 0. Okay. So 1 means the model is telling me, so this is called a model. This equation will be called the model. So 1 means the function is telling me that this person will probably pay his loans. 0 means the function is telling me that this person will probably not pay his loans. So I can easily rely on this function to tell me who will return their loans and who will not. So this is how predictions are made. We have a historical data based on which we find this function f, and then we take that function f and collect all the independent variables of future or new data, and then we find out the value of y. Okay, this is how all machine learning algorithms will work. Do you follow, guys? Doubts here? So we will evaluate different algorithms in details. Okay, we will evaluate how is this function f found, what are the challenges we face while finding this function. So all of this we will discuss in details. Okay. Yes, Hers, it is wrong a lot of times. That's what. So it can be wrong a lot of times. So we try to minimize the error. That is where the challenge lies in machine learning. We try to minimize the error, but it can be wrong. Many a times it is wrong. It goes horribly wrong. Okay, but we will see ways, or we will see, that is why we have different algorithms, right? We don't have just one algorithm because it can go wrong. So we have different algorithms, and each algorithm has its own strengths and weaknesses. So we will understand, and we will know which algorithm has what strength and what weaknesses, and accordingly we will plan. So depending on the data, we will choose an algorithm which suits the data best. And it is not easy, of course. It requires a lot of practice. It requires requires us to learn a lot of things about the algorithms, go deep into the maths of the algorithms and see why is the algorithm predicting what it is predicting. So it requires a lot of hard work there. But whatever the algorithms will predict will definitely be better than what a human would do. Okay, a human would take a lot of time and then predict something. An algorithm will obviously and most probably do better than a human does. That is why it is called machine learning, because you have trained your machine to do what a human otherwise would have done. So this is what is supervised learning. We'll be talking about supervised learning for the next maybe 5 or 8 classes, and then we will move to a few algorithms in unsupervised learning. We'll come back to supervised learning, so I will keep rotating between supervised and unsupervised. Okay, unsupervised learning is not similar to what we just saw. This is about finding patterns in the data. Okay, in unsupervised learning we find patterns in data. So here we do not have a dependent variable. There is no y here. So y is equal to fx. That kind of a relationship is not there. Here we just see the data and we try to find patterns within the data. Okay. So which data points are similar? So for example, on the same bank data set, we can try to find which customers are similar. So let's say we have 10,000 customers. So which of the 10,000 customers are similar? Or if you have to divide the 10,000 customers into different groups, why do you want to divide them into different groups? Because you may have some strategy for different groups. So you may have one strategy for one group, you may have another strategy for another group. So you may have different strategies, and accordingly you would want to target different customers based on your different strategy. So that is where you would want to divide your customers into different groups. So this is where unsupervised learning lies, finding patterns in your data and then creating groups within your data. Okay, we'll talk about this in details later, but this is high level what is unsupervised learning. Okay, so today we will start with our first algorithm in supervised learning. Now supervised learning again is divided into two parts. It is divided into two parts. One is called regression and the other is called classification. Have we covered all this, guys? Did I cover this in the last class? Okay, I have covered this in the last class. Okay, I'll just quickly walk through this. So supervised learning is divided into two parts. One is regression and the other is classification. So regression is where, so in both places we try to do the same. So supervised learning is all about y is equal to fx, where we try to find f. Okay. Now what is the difference? Why do we divide them into two classes? Regression is where y is continuous. Okay. So remember we had talked about the different types of variables used in statistics. So we have quantitative variable and we have qualitative, right? Within quantitative we have continuous, we have discrete. Within qualitative we have nominal, we have ordinal, right? So this is used for quantitative variable and more specifically for continuous variables. So wherever your y is continuous in nature, that is where you will call it a regression problem. So for example, it can be income. You are trying to predict the income of a person, or you are trying to predict the sales. You are trying to predict the volume of something sold, let's say volume of soft drinks sold in a market. Okay, you are trying to predict the price of a house based on the different features of the house. So all these will fall under regression cases. Okay, these are all regression cases. Now classification is where your y is nominal. Okay, for example, yes or a no. So the bank example that I gave you, that is a classification case, because the output can only be yes or a no, or 1 or a 0. Okay, that is a classification. Other examples can be, let's say, face detection. So when Facebook tags you, when you upload a photograph, that is nothing but a classification algorithm. Okay, it sees your face, identifies your face, and tries to match it with your name. Okay, so that is also a classification case, because you have several options, and out of several options, so here it is binomial in nature. For the bank example, this is a simple one where the output is binomial. It is either 1 or 0, but you can have more than 2 classes also. You can have as many classes as you want. So for example, for in reference to a stock, to the stock market, so whether you should buy a stock, you should sell a stock, or you should hold a stock. Okay, so there are 3 options here. So this is a classification problem. Yes, Arpita. Or for example, the Titanic example, the Titanic data, their passenger either survived or did not survive. So this is also binomial in nature. So we will mostly see binomial examples, because that is most popularly used. So whether the passenger survived the accident or did not survive the accident. Okay. So this is also binomial. Facebook face detection has several categories, one of which is true. So that is not binomial in nature. Okay, so all these cases will fall under classification cases. Now why we are learning them separately? Because we have different algorithms for them, and they work in different ways. We take a separate approach for a regression problem. We take a separate approach for classification problem. Okay, so the first algorithm that we'll be learning today is linear regression. Okay, so linear regression is one of the algorithms used for regression. As the name suggests, it is used for regression. So linear regression will fall here. So linear regression will be used only for regression problems in supervised learning. Okay. Now what is the speciality of linear regression? The speciality is this. So in both regression and classification, we are trying to find this function f, right? We are trying to find the function f in both the cases. In linear regression, what is the speciality? The speciality is that we assume that this function f is linear in nature. That is the speciality. We take a very simple assumption that this function f, which gives a relationship between the two, is linear. That is the assumption, and hence it is called linear regression. Okay, so if we have one y, and let's say we have just one x, okay, we have only one x, only one independent variable we have, then we will assume that the relationship is this: beta naught plus beta 1 x. This is the relationship we will assume, because it says linear regression, right? So the assumption is that it should be linear, and this is the linear relationship. Okay, so do you understand what is this? What is this, the equation? What is this equation? What is the structure of this equation? Yeah, this is the equation of a straight line. Okay, y is equal to mx plus c. So remember, in your high school you would have learned about straight lines, right? But you would have seen this equation: y is equal to mx plus c. Here the same equation I have written, instead of m I have written beta 1, instead of c I have written beta naught. So it is the same equation. Sinu, what is not clear? Which portion? Okay. So why did I write the equation of a line? Because we assume that the relationship is linear. We take a very simple assumption that in case of linear regression, the relationship between the dependent variable and the independent variable is linear. So that is a very simple assumption we make. Okay. So that is why I have written the equation of a straight line. So this will be true only if you have one independent variable. I have only one x, that then only it will be true. Now what happens if I have multiple independent variables? Let's say I have x1 and x2. I have two independent variables now. Okay, because my output may depend not just on one variable, right? It may depend on many other variables also. So the sales of a company will not just depend on the marketing budget of the company. It may depend on several other factors. So let's say it depends on two factors, x1 and x2. Okay, so how should I write this now? So the same linear line I will extend. I will write y is equal to beta naught plus beta 1 x1 plus beta 2 x2. Okay, same linear line I have extended. Now what is this a equation of? This is a equation of a straight line, you told me. What is this a equation of? Learn this in high school. Yes guys, what do you think this is the equation of? This is not a straight line, right? It's something else. What do you think it is? Recall from your high school days. So let me tell you, this is the equation of a plane. Okay, this is a plane. If you remember, the equation of a plane that you saw was ax plus by is equal to c. Remember, this is what you saw in your high school. So this is similar. Instead of c, I have written beta naught. Instead of a, I have written beta 1 x. Instead of b, I have written beta 2. And instead of y, I have written x2. So this is my x, this is my y. So this is the equation of a plane which looks like this, let's say, where this is your x1 and this is your x2. Okay, and any point here is your y. Okay, so this is the equation of a plane which is also linear. Notice this is also linear in structure. So if you have one independent variable, you assume the relationship to be a straight line. If you have two independent variables, you assume the relationship to be a plane. If you have more than two independent variables, the relationship will still be linear, but we don't have a name for that yet. So it will look something like this. Okay, beta n xn if you have n independent variables. So this is the general form of a linear regression equation. Okay, this is the general form. So this is how we assume the relationship between the dependent variable and the other independent variables in linear regression. Okay, is this clear guys? Any doubts? Any doubts guys so far? Okay, so let's proceed. Okay, so let's start with a few examples. Okay, so let us first start with a simple linear regression. So what is a simple linear regression? A simple linear regression is where you have only one independent variable. Okay, only one independent variable. This is just a simple one just for understanding. In the industry or usually you will never have one independent variable because your output will depend on several factors. But for understanding, let us start with one independent variable. Let us try to predict the price of a house based on the area of the house. Okay, area in let's say square feet. Area in square feet. Based on the area in square feet, we will try to predict the price of a house. Okay, I know the price of a house will depend on several other factors. It will depend on the location, on the number of bedrooms it has, okay, on the amenities that the house has, and so several other factors. But right now, for simplicity, let us just assume it depends on the area. Okay, total square feet, super built up area of the house. So I will draw the area on the x-axis. This is my x, and the price will be on the y-axis. Okay. And let's say these are the points I have. I have collected data of several houses. Okay, I have collected data of several houses and this is what I get. Okay, let me make it fewer so that it is easy to evaluate. Let's say I have collected data of four houses, house A, house B, C and D. Okay, now I have assumed that, or we have seen that there is a relationship between the two, and that relationship is the function f. Okay, that relationship is the function f between price of the house and area. Now sometimes it is very difficult to find this function f. Okay, it is difficult to find the exact function f. So what we do, instead of finding the exact function f, what we do, we find a function f dash instead. Okay, we find a function, or let me say not f, instead of finding f we find a function g which is very similar to f, which is very close to f, but has a small error. Okay, but has a small error. So this is where Hers was talking that our predictions can be wrong. Yes, they can be wrong. That is why, because we are not finding the function f, it is very difficult to find the exact function f. What we do instead, we find a function g which is very similar to f but has a small error. It has a small error component, and what we try to do, we try to minimize this error. We try to make this error as small as possible. Okay, we try to make the error as small as possible. This is what all machine learning algorithms will try to do. They will try to find, they will try to go very close to the function f, but sometimes it may not be possible to get the exact function f. So in that case they will find another function g which is similar to f but has a small error. Okay, so when we assume, so for example in linear regression, when we assume that the relationship is linear, now the relationship, the actual relationship may not be linear, it may not be a straight line, but if we forcefully assume that it is a straight line, obviously we will have some error. We cannot avoid. So for example, look at this data. We cannot draw a straight line through all the points. It is not possible. But we will assume that the relationship is linear. Okay. So if we assume that the relationship is linear and if we draw a straight line through this, we will have some error. Okay. But we will try to draw a line so that the error is minimum. The error is not a lot. Okay. So let's say I draw this line. I draw this line through the data. Okay. Now what are the errors I will get? So there are 4 points. So I will get 4 errors. I will get 4 errors. Let me call it error A, error B, error C, and error D. I'll get 4 errors because I have 4 points. So what is the error for point A? Yes, guys, what is the error for point A? What do you think? Yes, it is 0 because the line is passing through the point, right? So the error for point A is 0. Why it is 0? What will your line tell about the price at this area? So the area here for point A, the area is this particular point. So what will your line predict? Your line will predict this particular price, this PA. Your line will predict PA for this point, and the actual price is also PA. You look at the actual coordinate of the point. The actual coordinate of the point gives the actual price. Okay, the actual coordinate of the point gives the actual price, and the corresponding point on the line, gives the price that the line gives. Okay, and here both happen to be the same, so the error will be 0. So for point A you are not making any error because you are predicting exactly what the actual price is. Okay, now let's go to point B. So for point B, what will you predict? What will you predict for point B? Will you predict this? What will the line tell you? For point B, what will the line tell you? Will it tell this or will it tell this? This one or this one? First or second? First or second? No, it is the second. Okay, Bharti, it is the second. The line will always predict whatever is coming on the line. It cannot predict something which is outside the line. So the line, even for point B, will predict this particular point. The line will predict this because this is where the line lies, right? The line cannot predict here. It can only predict on the line, not outside the line. Okay, so for this, the line will predict this particular point, but the actual price at point B is this. This is the actual. So that means we have an error here, right? We have this much error. So this is the error we are making. This is error for point B. Okay, so we do have, so let me write it like this: actual minus predicted. What is predicted? Predicted is what is coming from the line. Okay, this is the actual coordinate. Okay, so here actual minus predicted, you will get some positive quantity, right? You will get some positive quantity here, actual minus predicted. So the line is under predicting. It is predicting less than what the actual price is. Okay, do you follow? This is the error. So how did I find the error? I just took the distance parallel to the y-axis between the actual and the predicted. Okay, parallel to the y-axis. Remember, I have taken parallel, not perpendicular. I have taken the distance parallel to y-axis. Why parallel to y-axis? Because my y-axis is the dependent variable. I'm trying to find whatever is on my y-axis. So I will take parallel to y-axis. Okay, so this is my error B. Similarly, what will be error C? Now at C point also you can see the line passes through the point. So here also the error is 0. We are making 0 error at C. Okay, we are making 0 error at point C also. Now finally for point D. Now let's find the error for point D. So for point D, the actual coordinate is here. So this is the actual price for point D. But what are we predicting? We are predicting somewhere here. We are predicting more than the actual value. So the actual price of the house is lesser, but we are predicting more. Okay, so we are predicting this is price at D. We are predicting this, but the actual price is more than what we are predicting. So here also we will write actual minus predicted, which is, since actual is more, no, our predicted is more, sorry, I made it wrong. So the actual is less. The actual is somewhere here because this is the point D, but we are predicting more than the actual. We are predicting this particular point, but the actual price is only here. So here actual minus this will give you a negative value. Okay, this is the error. This is the error at D. You are predicting this point. Sorry, you are predicting this point. This is your prediction, and this is the actual coordinate of the point. So you will get a negative quantity here. Okay, so these are the errors that this line is making. Now you see, when we assumed that the relationship is linear, we are getting some error. We are not getting perfect prediction, we are getting some error. Doubts, guys? So look at this, tell me if you have any doubts here. Yes, Bharti, that is true. Though you have one independent variable, you have two errors. Errors do not depend on the number of columns you have. Okay, it depends on the number of rows you have. So actually, we got four errors, one error for each point. Okay, two of the four errors happen to be zero. Okay, so your errors will be on the number of houses you have, not on the number of areas you have or the different features that you have. Okay, it will be on the number of rows, not number of columns. You will have as many errors as the number of rows, because for each house, so you have four houses in your data A, B, C, D. For each house you are predicting its price. So for the first house there is some actual price and you are predicting some price. Similarly for the second house there is some actual price, you are predicting some price. So the errors that you will have is on the houses. Okay, so let me show it to you. So let's say this is house number. Okay, you have A, B, C, D. Okay, this is the area of the house. So whatever is the area, let's say I have written some numbers. Now this is actual price. Okay, and this is predicted price. Okay, so actual price is, let's say, 10 lakhs, 12 lakhs, 15, 25, and you have predicted something here. You have predicted something. So how many errors will you have? You will have four errors. For each of them you will have one error. So 10 minus this quantity, 12 minus this, you will have some EA, EB, EC, ED. So this error has nothing to do with this area. Okay, even if you had, let's say, one more feature, let's say number of BHK, how many bedrooms does it have, even then you would have the same number of errors. So the point I'm trying to make is the number of errors will not depend on the number of columns you have. It will depend on the number of rows. Okay, for each row you will have one error because each row talks about one house. So this first row talks about house A, the second row talks about house B, the third row talks about house C, and the fourth row talks about house D. Okay, any other doubts? Okay, Now let us see how do we evaluate the error. So we saw that we are getting some errors, but how do we understand the error? This is also very important, because let's say if I have 10,000 houses, if I have 10,000 houses, I cannot I cannot find out 10,000 errors like this. If somebody tells me that he has built a model, he or she has built a linear regression model, then obviously the question that will be asked is how much error is your model making, right guys? Because everybody might come up with a different model, right? So how will we compare how much error everybody's model is making, right? We have to compare whose model is the best. So how will we compare? If you have 10,000 houses, we will get 10,000 errors, right? We will have error A, error B, and till 10,000. Till 10,000 you will have error. Similarly, any other person also who has built a model, he or she will also have 10,000 errors. Now how will you compare which model is the best? Is model 1 the best, or is model 2 the best? So with 10,000 numbers it is very difficult to compare, right? So person A will have 10,000 numbers, person B will have 10,000 numbers, but we cannot compare all these numbers together, okay, one on one. It will be very difficult. So we need some parameter to describe the error as one number, so that it is easy to compare, okay? Because we cannot compare with 10,000 numbers. So let's say somebody has taken 10,000 houses and then predicted. Somebody has taken, let's say, only 8,000 houses. So then this person will have only 8,000 errors. This person will not have 10,000 errors. This person will have 8,000 errors only. But that doesn't mean his model is good or worse than the other. It's better than the other or worse than the other. It doesn't mean that. Okay. So for example, let's say this is a model. This is price and this is area. Similarly, I have another model here. This is area and this is price. Let's say this is 3 points here. I have the same 3 points here, but I have some additional points also. Okay, I have some additional points also. And this is the model that I have drawn. Okay, this is my model here. And similarly, this is my model here. Or let's say this is my model here. Now, which one of this is better? Model 1 is better or model 2 is better? What do you think is better? Which one of these is better? Is a better model? Why 2? Bharti, why 2? Okay, Harsh is 1. So why do you think 1 is better or 2 is? Okay. Sinu says more points are covered in second. Anupama says it is near to actual. Okay. So the answer to this is you cannot say. You cannot say which one is better. Okay. It is very difficult because they are so this model is built on 3 points. This model is built on more than 3 points. So you cannot say which one is better unless you find the errors. Okay. Unless you find the errors, you cannot say which model is better. Okay. So let's say these two models were built on the same data. They were built on the exact same data, but this was built on just 3 data points and this was built on 6 data points. Okay. But these 3 data points, if you see, they are the same. So this is also built on ABC and this is also built on ABC, but it has some additional points also. So this person selected 6 points, this person selected only 3 points. So you cannot say which one is better looking at this figure. Okay, you will have to find out. And how will we find out? So let's say we will find the errors. We will have EA, EB and EC. 3 points here. Similarly, we will have EA, EB, EC, ED, EE and EF. We will have 6 errors here. Now how will you compare? Because you have 3 errors here and you have 6 errors here. So obviously the error here will be more. because I have more points, because each will, even if the errors are small, since there are 6 points, they will add up to become a big number. And since there are only 3 points here, this will not add up to be as big a number. So if you look just the errors, if you look just the total error, for example, sum of the errors, you will feel that both of them are different, and this one has lesser error than that. But that doesn't mean this model is better. This model is better, or it has lesser error, only because it took fewer points and because this model took more points. But that doesn't mean this model is worse than this. Okay, so the answer is we cannot say which model is better. Okay, we need parameter. So that is where we need a parameter which will tell us what is the total error in a model. Okay, what is the total error in a model? So before we start analyzing the errors, let us first discuss how do we get that straight line. So you may be wondering, right? Why did I draw a line like this? Why did I draw a line like this? Why not something else? So why didn't I draw a line like this? Or why didn't I draw a line like this? Or maybe like this? I can draw infinite number of lines, right? Through the same number of points, I can draw infinite number of lines. So how did I decide which line to draw? So let us talk about that. Okay. So what have I written? I have written ordinary least square. What does it mean? So this is the name of an algorithm. Okay. Ordinary least square, or OLS, is the name of the algorithm that is used to find the straight line. What is the straight line which gives the least amount of error? Because that is our goal, right? Our goal is to minimize the error. So what is the straight line which gives the least amount of error? That is given by ordinary least square. Okay. So how do we find which is the best line? So let me ask you through an example. So let's say this is point A, this is point B, and this is point C. Okay, so this is line number 1, this is line 2, this is line 2, and let's say this is line 3. Okay, now which of the 3 lines do you think is the best? For these 3 data points, which of the lines do you think is the best? No, tell the color, Arpita. I have not given numbers to the line. Which color? Green, pink, blue. Okay, Harsh says the blue line is the best. Okay. Okay, Arpita also says the blue. Okay, let's see which line is making what error. Okay, so let me give coordinates to the point. Let's say this is 10, this is 5, let's say this is 2.5, this is, let's say, 7.5. Okay, this is your y and this is your x. So let's find the actual value, and let's find the predicted value, and let's find the error. Okay, actual, predicted, 1 second, let me find it here. So I'll write the actual value, I will write the predicted value, and I will write the error due to blue line. the error for the green line and the error for the pink line. Okay, I have 3 points, so everywhere I'll have 3 errors. Okay, so point number A, point number B, and point number C. Okay, so guys, tell me what is the error for point A? What is the actual value of point A? What is the actual value of point A? Yes, 7.5. Actual value of point B is 2.5 and point C is also 7.5. By actual value I mean the actual Y. Okay, because we are talking about Y, right? We never talk about X. We are trying to find the error in Y, in our dependent variable, not in our independent variable. Independent variable we already know. Okay, so let's find the predicted value. Okay, this column is not needed. Let's find the predicted. Okay, it is needed actually. Let's find the predicted value for blue, for the blue line. What is the predicted value for point A? For the blue line. Same means what is the value? 7.5. For the blue line, it is 2.5, right? It is here. Okay, it is 2.5. Similarly, predicted value for point B, it is 2.5 again for the blue line, right? And for point C, it is 7.5, right? Right, guys? Do you agree with this? Okay, so what is the error? The error is 5 here. The error is 0 here. The error is 0 here, right? So the total error in blue line is 5. So if you take the summation, you will get a total error of 5 here, right? Now let's compute the same for the green line. Okay, so I'll just erase this. I'll write it now for the green line. So what do you think is the predicted value for point A, for the green line? For the green line, what is the predicted value for point A? Okay, 5. Yes, it is 5. For point B, for point B, again 5. Yes, for point C, it is 7.5. So if I write the error, it is actual minus predicted, so 2.5. Again actual minus predicted, so minus 2.5. Again actual minus predicted, so 0. So what is the summation of error for the green line? It is 0. Okay, it is 0. Similarly for the pink line, let's compute for the pink line now. So I'll erase the predicted values of the green line and write for the pink line now. So what is it for the pink line? Point number A, how much is it predicting? 5. For the B point, all 5. Yes, because this line is parallel to the y-axis, so every time it will predict 5. At every point on this line, the value of y is always 5. Okay, so the error is 2.5 minus 2.5 and then again 2.5. So the total error is 2.5. Okay, so which is the best line then? Which is the best line as per this? The green line, right? The green line is the best. But do you think the green line makes 0 error as we get here? Do you think that the green line makes 0 error? We are getting a total error of 0. Do you think it is making 0 error? No, it is not making 0 error. It came 0 only because one error was positive and one error was negative, and it cancelled each other. But actually the green line is also not making 0 error, though it is making the least error. It is making the least error out of these 3 lines, but it is not 0. But here we are getting 0 because they have cancelled each other. Okay, so then how do we decide which line is the best? How do we decide which line is the best? That is where ordinary least square comes into picture. Ordinary least square tells us that the best line, or the line of best fit, is the line with minimum SSE. Okay, what is SSE? Sum of squared error. Okay, that line is the best. The line which has the least value of sum of squared error, which is this. So any line which gives the least value of this quantity, whatever I have written here, that line is supposed to be the best line. Okay, so this line, the line which has the least value of this, that is the best line, is what the algorithm tells us. Okay, and why it tells us square? Why does it square? Because otherwise it might cancel each other and we may think that this line is the perfect line. So look at the issue that we faced here. We were thinking, looking at this 0, that this line is the perfect line, it has 0 error, but actually it does not have 0 error, it does have some error. So to remove that misconception, that myth, we take the squared error so that the signs remain the same. The positive and the negative do not cancel each other and we get some amount of error. Okay, otherwise we will always think that it has 0 error, but actually it will have some error. Okay, so now let us take the square of this. Instead of error, let us take the square. So 2.5 whole square, we will get 6.25, right? 2.5 into 2.5, we will get 6.25. Similarly here also we will get 6. Let me write it again. So for the green line, the error that you will get is 2.5 into 2.5 for point A, E1 square plus EB square plus EC square. How much will you get for the green line? 1 second. I'll leave it as it is so that it is easy for us. Now we can compute for the green line. So what is the sum of squared error for the green line? For the green line, what is SSE? It is EA square plus EB square plus EC square. What is EA square? 25 into 25 is 125. So 12.5 for point A. Again 12.5 for point B. And point C is 0. Right? So it is 25. Actually it is 25. The error of the of the green line is 25. Let us find for the other lines. Let us find for the blue line now. So what is the error for the blue line? The total error, the total sum of squared error for the blue line. Okay, this is 6.25, right? Not 12.5. 25 into 25 is 6.5. Okay, sorry. So it is 6.25. It is 6.25 and 0. So you will get a total of 13. No, 12.5. You will get a total of 12.5. Okay. So for the green line, the total error is 12.5. Okay. Let's calculate for the blue line. For the blue line, what do we have? So EA square is 25, EB square is 0, EC square is 0. So the total error that we are getting is 25. Okay. Similarly, let us calculate for the pink line. For the pink line, SSE is 2.5 square, which is 6.25, again 6.25, and again 6.25, right? So 12.5 plus, it will give 18.75, right? Right, guys? So these are the errors that we get, and which line is the best. So what did we learn here? That line of best fit is the line with minimum value of sum of squared error. So which line turns out to be the best line? It is again the green line. It is again the green line, but this time we have some error also. We have some value for error. So now we are sure that this line is not perfect. So this way of analyzing is better than what we used previously. So we never use E1 plus E2 plus En to find out the best line. What we use is E1 square plus E2 square plus En square. Always remember this. That is what the algorithm tells. It is not E1 plus E2 plus E3. It is E1 square plus E2 square plus E3 square. So we always analyze the sum of squared error. We always analyze the sum of squared error and not the sum of error. So always remember this. Okay, so the ordinary least squares algorithm tells us that the line of best fit is found by minimizing the sum of squared error. Okay, is it clear? Any questions do you have, guys? Tell me, guys, if you have any questions here. Okay, so this is what the ordinary least square tells us. Ordinary least squares is an algorithm that is used to find the line of best fit, or which is that best line which has the least amount of error. So how do we decide the least amount of error? We decide the least amount of error by using the sum of squared error and not the sum of errors, because if we take the sum of errors, we might fall into a situation where some positive error is completely cancelling out some negative error and we are getting a zero error, but actually that error would not be zero. So to remove that confusion, we always take the sum of squared error and not the sum of error. Okay, so any line which gives the minimum value of sum of squared error is the line that we should take. Okay, there is no other criteria to find the best line. It is always the sum of squared error. This is what the algorithm tells us. Okay, so let's take a break at this point. After the break, we will see some other parameters. We will see why sum of squared error is also not very good. There are a few disadvantages of sum of squared error also. So we will try to study those disadvantages, and we will see some other parameters which will be used to remove those disadvantages. Okay. So let's. Yes, yes, Anupama, that is also true. We are also increasing the error value, but that is required, right? That is a necessity, because if we don't do that, the errors might cancel each other and we might misbelieve that there is zero error, which is also a bigger problem, right? You should never misbelieve that your error is zero. And for comparison purpose, you can do that, right? Because you are squaring and increasing the error of not just one line but all the lines. So all the lines, their error will be increased. So you can still compare them. So let's say 5 and 6. If I ask you which number is greater, is 5 greater or 6 greater? Which number is greater out of 5 and 6? So obviously the answer is 6. So how did you find? You can compare 5 and 6 directly, or you can compare 5 square and 6 square also, because you are giving equal treatment to both. So even 6 square is greater than 5 square. So similar logic. We cannot use 5 and 6 directly because they might give you we cannot use the sum of error directly because it might give us 0. No, blue and green are not having same value, Harsh. We just saw, right? Blue and green are not having the same value. The green is having the least value. Green is having 12.5. Blue is having 25. Double of it. They are not same. The least one is the green one. Okay, Harsh? Yes, I'm talking about SSC. This is the SSC, right? This is the SSC that we have calculated. It is 12.5 for the green line and it is 25 for the blue line. So the green line is lesser. The sum of squared error for the green line is better. That is why I say the green line is the best line. It is not same. Do you follow, Harsh? Okay, so what did we see so far? So let's quickly review whatever we discussed about linear regression. So linear regression is one of the algorithms in supervised machine learning. Okay, supervised machine learning means where we try to find a relationship between dependent variable and independent variables. Okay, and in case of a linear regression particularly, we assume that the relationship is linear. Okay, we assume that f is linear in structure. So that is why we assume that the relationship is beta naught plus beta 1 x1 plus beta n xn. This is the relationship that we assume. Let me write y hat. Okay, instead of y I am writing y hat. What is y hat? Y hat is the predicted value. Okay, y is usually used for the actual value. Okay, y is used for the actual value and y hat is used for the predicted value. So I should put y hat here instead of y, because this is the equation to get the predicted value, not the actual value. Okay, so and the error is actual minus predicted, or y minus y hat. Okay, and we saw the ordinary least squares algorithm, right? We saw the ordinary least squares algorithm. What does it tell? This tells us that the best line is line which has, or we try to minimize the sum of squared error, and that is how we get the equation of the line. Okay, so while doing this we get to know the equation of the line. Okay, all clear so far, guys? Please respond. Okay, okay, now we can use sum of squared error as a parameter to evaluate our model. So let's say some of you have built a model which is model 1 and some other of you have built another model which is M2. Okay, now some of you have got SSC1 and some of you have got SSC2. Can I directly compare these two and tell which model is better than the other? Can I do that? Yes or no? Okay. Okay, so this is a little tricky because the answer depends on whether we have taken the same number of rows or not. Yeah, we just did. We just did. Okay, we just did. We just compared SSC1 and SSC2, but we can only do that if they are built on the same number of rows, not otherwise. Okay, so imagine, so just to give you an example, let's say I have this model and the same data I'm writing here, A, B. I have A, B, C, D, E. So I have this as the data and this is the data. A and B are same in both the data sets. Okay, so I have built a model here and I have built another model here. Okay, now which one has, let's find the SS sum of squared error for this model. What is the sum of squared error for this model, guys? 0, right? So 0 square plus 0 square is 0, and sum of squared error for this model, it will be error due to B whole square, right? All others are 0. Am I right? All others are 0. Just for B you will have some error, right? Just for B you will have some error. Now which model is better? If I ask you the same question again, which model is better? What will you say? Is this model better? Is 1 better or is 2 better? Bharti says 2 is better. What about others? Harsh says 1 is better. Okay. Okay, so okay guys, this is a little tricky, so pay attention. Okay, that is why intentionally I kept this after the break. No, Bharti, it does not have large number of variables. It has large number of rows, observations. Rows are observations. Variables means columns. Both of them have just one column. Okay, both of them have the same number of variables, which is y and x. Okay, number 2 has more observations, more rows. Okay, so your data is like this: A, B, C, D, E. These are the rows you have. Okay, okay, so now what we have to discuss is which model is better. Can we decide which model is better? So let's say somebody, you were given these 5 rows. You were given these 5 rows of data. Half of you, what you did, you did not take all the rows. You just took row number A and row number B. You just took 2 rows and you plotted this model. Okay, and what others did is they took all the rows and they plotted this model. Okay, now my question is, which of the two models is better for all the data, not for just A and B, for all the data? Which of the models is better? Is this model better or is this model better? So now what do you think, which model is better, 1 or 2, on all the data, not just A and B? Yes, probably 2 is better, right? Because if I put these points here, I will get somewhere here C, D, and E, right? The C, D, and E, which these guys have not used here, is probably somewhere here. So you see the error. These will have a huge amount of error, right? They will have a huge amount of error. But if you just look at SSE here, you will think that the error is 0. But actually it is not 0. They have avoided some points just to get a 0 error. So what does it mean? This means that this is better, right? This is better. This SSE is better. So the second model is actually better than the first model. But why did we get a lesser error for the first model because we took less number of points, right? Because we took less number of points, that is why we got a smaller value of sum of squared error. So the point I'm trying to make is you can only compare the sum of squared error if you are predicting for the same points, if you have the same number of rows, if two models has the same number of rows and two models are predicting for the same points, only then you can compare them, otherwise you cannot. Okay, do you get this, guys? So this is the point I'm trying to make. SSE depends on the number of observations. So if somebody has taken less number of observations, obviously his error will be lesser. And if somebody else has taken more number of observations, obviously his or her error will be more. Not because the model is bad, just because he or she has taken more number of observations. And even small errors will add up. So, but that does not mean the model is bad. Only because the second time more data points were taken, more observations were taken, the error has come to become a bigger number. But it is not a bad model. Are you getting this, guys? Okay, so that this is one major drawback of using SSE. This is one major drawback of using SSE to compare models. This is why we do not use sum of squared error to compare two models, because what if the models are predicting on different number of rows? We don't know, right? The models might be predicting on different number of rows, or they might be predicting on the same number of rows but on different rows. So for example, this model might be predicting on row number A and B. Let's say if you take only C and D and build a model, but C and D are different rows, they are not same as A and B, so you cannot compare the error made in A and B with the error made in C and D. Only if the number of rows are same, and only if both models are predicting on the same rows, only then you can compare them. Otherwise no, otherwise that will not be a good comparison. Okay, do you get me, guys? Are you following? So if this is, so I'm writing the error due to model A. For A, I will have some error. Let's say I have one, I have two, and I have not used these data points to predict for this model. Similarly, let's say again I have taken two data points. Let's say I have got 3 and 4 here, and I have not used the other data points. So can I compare these two errors? Let's say these are sum of squared errors. Can I compare these two? No, I cannot, because this is predicting on data point A, this is predicting on data point B, and whereas these two are predicting on these two data points. So I cannot compare them. I cannot compare them. And I have not written 0 here, okay? I have written not available. That means I have not used this. I have not used this. Okay? So I cannot compare them because they are predicting on two different things. It is like comparing apple to oranges. They are predicting on rows A and B, and this is predicting on rows C and D. So I should not compare them. Okay, or even if I have, let's say, something here, still this will not be a good comparison, because this model is predicting on 4 data points, whereas this model is predicting only on 2 data points. So obviously the error here might be larger than the error here because of the number of points involved. See, because it is E1 square plus E2 square plus En square. So it depends on the value of n, where n is your number of rows. It depends on the value of n. So the point I'm trying to make is sum of squared error, it depends on the number of observations. So you cannot directly use sum of squared error to compare two models, unless of course both the models are predicting on the same number of rows and they are predicting on the same rows, not just the number of rows but the exact rows also. Only then you can compare. So this is a problem, right? Because we don't know who is predicting on which row. So again, that there will be a confusion. You will have to ask on which rows are you predicting, on how many rows are you predicting. So there will be a big confusion. So to avoid that, we have some other parameters. We have some other parameters which are also used to evaluate a model. Okay, which are also used to evaluate how good a model is. Okay, so the first of that parameter is called root mean square error, RMSE. Okay, the first of such parameter that is used is called root mean square error. Now why do we need root mean squared error? We need root mean squared error because of the problem that we discussed with sum of squared error. Because sum of squared error, it increases as the number of points increases, but that does not mean the model is bad. It is only giving a high value of SSE because there are too many points involved, not because the model is bad. Okay, so that is why we have another parameter which is root mean squared error. Okay, and there is one more reason why sum of squared error is not used, because the units are also squared. So you see, when you for example, when you predict the price of the house, what will be the unit of the error? Actual price minus predicted price, whole square, right? You are doing a square here. So square means you are taking square of rupees, so INR square. That means your sum of squared error will have a unit of INR square. Now if somebody asks you what is the error your model is making, what will you say? You will say my model is making 500 rupees square. Now that also doesn't make sense. 500 rupees square, what is that? Nobody will understand what is 500 rupees square. So the units also do not make sense. So which is why we do not use sum of squared error to evaluate a model. So remember, we will still use it to find the best line, because that is the algorithm OLS. We cannot avoid that. We will use sum of squared error to find the best line, but we will not use sum of squared error to evaluate the line. How much error is it making? To find the amount of error the line is making, we will not use SSE for that. We will use something else. But to find the line, we will still use the same. Okay? Are you getting, guys? Is it clear, guys? Okay. Yeah, sure. So let me briefly write. First is what we discussed. It depends on the number of points. Okay. Depends on number of observations. So you will never know how many observations has the person used. If you have built several models, you will have to keep a note of how many data points were used in each of the model, which will be tedious. So that is why it is not used. And the other reason is units are not interpretable. Okay, the units are not interpretable, so this is another reason why it is not used. Okay, these two reasons. So now let us see how do we overcome those. how do we overcome those disadvantages? Okay. So root mean squared error, just like this is very similar to what we saw standard deviation. It is very similar. RMS, you see the word RMS again. In standard deviation also you had the word RMS, right? So again we will start from the right hand side to compute this quantity. So first we take the error. So how you take the error? You take y minus y hat, right? Actual minus predicted. Then you square it. So I will square it. Then you take the mean of it. So you divide it by n, and then you take the root of it. So I'll take the square root of it. So this is how you find root mean squared error. Okay, this is root mean squared error. Now if you see this carefully, we have n as the denominator. We have n as the denominator. So if so, that means you are dividing it by n. You are taking the average error. Okay, root mean, root average squared error. That means you are taking the average error. So this is not dependent on n, because if somebody takes 3 points, he will divide by 3. If somebody takes 5 points, he will divide by 5. So it will get normalized. It will get normalized, and what you will get is an average number, that this is the average amount of error your model is making. So this can be compared irrespective of the number of points you have used. Okay, so this can be compared irrespective of the number of points that anybody has used. So this can be directly used to compare multiple models irrespective of the number of points that has been used. Okay, do you follow? Yeah, of course, Arpita. It has to be used on the same data set. Now, somebody is predicting price. You cannot take a different data set and predict the volume of a company. Okay, it has to be on the same data set. Okay, but this does not depend on the value of n. So if somebody has taken 1000 points and somebody else has taken 10,000 points, you can still compare because you have divided it by n. So the person who has taken smaller number of points will divide it by a smaller number. The person who has taken larger number of points will divide it by a larger number. So it is the average error. On an average, for each point, how much error is your model making? It is that quantity. Okay, so it is irrespective of the value of n. And it has one more advantage. You look at the units now. Since we have taken the square root, the units will also be interpretable. So if you are predicting the price of a house, the units will be INR. The units will be in rupees, so there is no confusion. Also, you can easily say that I have built a model which predicts the price of a house and the error is 10 rupees. That means, or the error is, let's say, 10,000 rupees. That means if the actual price is 1 lakh, the price you predict will be either 1 lakh 10,000 or 99,000. No, 90,000. Okay, so 1 lakh plus minus 10,000. This is the error. So on an average, your model is making an error of 10,000. This 10,000 is the RMSE. Okay, so it is in rupees. It is in rupees, so you can easily compare. So that is the advantage of RMSE, both in terms of two advantages. Again, both the disadvantages are removed now. The disadvantage of not being interpretable and the disadvantage of depending on the number of points. Both are removed when we take root mean squared error. Okay. Okay, cool. So this is all about RMSE that you need to know. We will calculate all of this in Python. We will learn that on in the next class. Today I just want to focus on the theory. This is very easy to do in Python. Don't worry about that. So this calculation you just have to subtract and take the square and divide by n and take the square root. You can easily do in Python. Now, but RMSE also has one disadvantage. Okay, RMSE also has one disadvantage. Let's say if you tell somebody that my RMSE value, oops, if you tell somebody that my value of RMSE is let's say 10,000. If I tell you that I have built a model and the value of RMSE is 10,000, will you be able to tell me whether the model is good or not? If I just give you this information that my root mean squared error is 10,000, can you tell me whether this model is good or not? Will you be able to tell me whether the model is good or not? If I tell you that RMSE is 10,000, what do you think? I don't give you any other information. If I just tell you that my root mean squared error is 10,000, can you tell me whether my model is good or not? No. Let's say not just see, Arpita, you don't have to just compare with other models. Let's say you have only one model. You have only one model, and you want to show it to your client, or you want to show it to any person, and you are telling that 10,000 is the error that my model is making. Now, will somebody be able to tell whether this model is good or not? We have just one model, let's say. Okay, so the question that you will probably ask is 10,000 is the error that your model is making with respect to what, right? 10,000 INR. Let's say you are trying to predict the price of house, and 10,000 INR is the error. So, but you will ask with respect to what? What is the actual price? Only then you will be able to say whether 10,000 is a good number or not. Let's say the actual price of the house is 1 crore, and then your model is 10,000. Then is it a good model? If the actual price is 1 crore and the error that you are making is 10,000, then of course it is a good model, because you are just 10,000 away from 1 crore. But if the actual price of the house is 10,000, let's say, and your error is also 10,000, is this a good model? If the actual price is 10,000 and your error is also 10,000, then this is not a good model, because the actual price is 10k and you are predicting plus minus 10k away. That means you are either predicting 0 or 20k. So this is a very bad model. But if the actual price is 1 crore, you are predicting 99 lakh and 90,000, right? Or you are predicting 1 lakh 10,000, 1 crore 10,000. So it's a good model. So the question that you will have to ask is with respect to what? Whenever somebody says that root mean squared error is 10,000, you will have to ask with respect to what? Only then you will be able to say whether it is a good model or not. So this alone is not self-sufficient, is what I'm trying to say. Okay, because we will always have to compare this with respect to the original price. Only then we will be able to say whether it is a good model or not. So this is the disadvantage of root mean squared error. Okay, so to remove that disadvantage, we have another error which is called mean absolute percentage error. Now we will compare the error as a percentage. Then this disadvantage will be gone. So let me write the formula again. We start from the right hand side. First we compute the error, so actual minus predicted. Then we take the percentage by dividing it by with the actual value. Okay, this is the actual value, and then take the absolute of it. So I take the absolute of it, and then I take the mean of it, so I divide it by n. Now this answer will be as a percentage. So for example, you will get, let's say, 5%. Now can you tell whether the model is good or not? I give you a model which makes 5% error. Can you tell me whether the model is good or not? Yes, you can tell me. 5% is very small. So that means if the actual value is 100, you are predicting 105. If the actual value is 10,000, you are predicting 10,500. So it is a good model. No matter what actual value you have, you can easily estimate the predicted value. You can easily estimate the error that you are making because you have given this as a percentage. Okay, so obviously you will have a very good idea of the error. What is FDR, Bharti? FDR, false discovery rate. No, we will talk about that later. That is used in classification. Okay, we'll talk about that later. This is regression. Okay, so mean absolute percentage error has the advantage that you will get the answer as a percentage. So when you get the answer as a percentage, you can easily evaluate your model without any comparison, that okay, 5% error whether it is good or not, 10% error whether it is good or not. So if you are okay with 10% error, you approve the model. If you are not okay with 10% error, you reject the model and tell the person to come up with a better model with less than, let's say, 8% error. But you can easily estimate. You don't need the actual values. But if somebody gives you the root mean squared error, you don't get it as a percentage term. You just get the direct units, that this is the absolute value of error that your model is making. But just looking at the absolute value, sometimes it is difficult to judge whether the model is good or not, because you will have to make a comparison with the actual price or the actual value. Then only you will be able to compare that okay, the actual value is very big, the actual value is in lakhs, and whatever error you are getting is in thousands, so probably it's a good model. But if the actual value is also in thousands and the error you are making, the root mean squared error you are making is also into thousands, that means it is not a good model. But if you take the mean absolute percentage error, you will directly get a percentage and you can easily evaluate. So that is the advantage of using mean absolute percentage error. Okay, so these are the three error terms that we have, each having their own advantage and disadvantage. One is sum of squared error, one is RMSE, and the other is mean absolute percentage error. You have a lot of others also. You have mean absolute error also, where you take the error, you take the absolute, and you take the mean. You don't take the percentage. But these three are most popularly used. We usually use MAPE and RMSE the most. Yeah, you can use that. So that alone is self-sufficient, but we anyways, it is not difficult to calculate, so we give this quantity also, because sometimes the absolute units also matter. We may not always want as a percentage, we may want the actual units also, that with what unit is the error coming. Yeah, I will give this in the assignments, Bharti. So I will have an actual data set where you will have to compute this in the assignments. Okay. Okay, so these are the three errors that are used. So this is used not just for linear regression. Whatever we have covered today is not used just for linear regression. It is used for all regression models. So linear regression, decision trees, random forest, whatever we will learn later, will all require these information. These same error parameters will be used for other algorithms also. This is common for all regression. So we will talk about this again and again. So don't worry, if you did not understand today, you will anyways understand, because we will every day talk about this. Whenever we evaluate any model, whenever we evaluate any regression model, we will talk about these parameters: root mean squared error, mean absolute percentage error. Okay, so remember, SSE is used to find the line. This is used to find the line because that's what the ordinary least squares algorithm tells us. It is used to find the line. This is used to evaluate the line in absolute units. Okay, this is used to evaluate the line as a percentage. Okay, so these are the advantages of the different error parameters that we have, which is true for all regression models, not just linear regression, all regression models. Okay. Okay, now coming to the last topic for today. So you might be wondering, right? So we discussed the ordinary least square. So let's dive a little bit into the maths of linear regression. Okay, we will see a little bit of maths of linear regression. So we have seen that we find the line of best fit by minimizing the sum of squared error. Right? We minimize this quantity, and that is how we find the line of best fit. So let us see how actually that happens. How does the software do that? So this is what the algorithm states. So I can also write this, and we know that y predicted is beta naught plus beta 1 x1. So I'm only doing it for one variable just for simplicity. So I minimize actual minus predicted whole square, right? This is what I'm trying to minimize, summation of this. Okay, so I will try to write this like this. So my actual value is my actual value, and my predicted value is beta naught plus beta 1 x. Okay, this is my predicted value, right guys? Do you follow all this? Do you follow this till now? Okay, this is my predicted value. Y hat is my predicted. Okay, now what are the unknowns here in this equation? What do you think is unknown when you start doing linear regression? What is unknown to you in this equation? What is unknown in this equation? Actual value? No, actual value is also known because you are dealing with historical data, Bharti. You are dealing with historical data where you know the actual value. Remember the bank example from 2010 to 2018. You know the value of Y, you know the value of everything. Okay, Amit says constants beta naught. Yes, exactly. Naresh is right. We do not know what is beta naught and what is beta 1. That is why we are doing linear regression, right? Because we want to find these two. Y and X is already known to us, right? You already know the price. You already know the price of house. You already know the area. What you don't know is the function f, which maps the two. Yes, Arpita. So these two are unknown to us. So that is why we are doing all of this to find beta naught and to find beta 1. So how do we do that? Let's see the maths. So I've written this minimize thing. Now, how do you minimize a function? So remember your high school thing once again. How do you minimize a function? Let's say this function is f of x, let's say. How do you minimize a function f of x? How do you find the minimum of a function f of x from your high school? Remember your high school days, we take the differentiation of the function and we make it 0, and then we find the value of x. Remember this? We differentiate the function and then make it equal to 0, and then we solve for x, and whatever value of x we get, that is where the function is minimum. Remember this? This is high school. In class 9th and 10th, you studied this. Yes, that is correct, Arpita. Okay, so this is what we used to do in school, and that is what we will do here. We will differentiate this and we'll make this equal to 0. But here, see, in high school, you just had one variable x. So you differentiated with respect to x. You took ddx of f of x and you made it 0 because your variable was x. Now, what is your variable? You have two variables now, beta naught and beta 1. These are the unknowns. So you will do d of d beta and you will do d of d beta 1. Two differentiation you will take. You heard of the term partial differentiation? That is what you will do here. You will differentiate this quantity once with respect to beta naught and once with respect to beta 1. Okay. So this is the calculus that you will do, or the software does this, and then you have two unknowns. You will get two equations here. By differentiating, you will solve the two equations and you will get the value of beta naught, and you will get the value of beta 1 also. After solving these two equations, you will get the values of beta naught and beta 1. So that is how the software calculates. Okay. So we'll not go into further details of the maths. I will not do it manually and show it to you. But if you do this, you can get the values of beta naught and beta 1. Okay, so this is the maths behind linear regression. Do you follow this, guys? Any doubts on this, guys? No, nothing. After that, then you know the equation of the line. That is your goal, Arpita. So after you calculate beta naught and beta 1, which is your C and M, you are done. You have your equation of the line now. So you have your prediction is equal to beta naught plus beta 1 x. Now in your next, when you receive your new data, you will receive only x. You just put the value of x and you get your y. So you have built a machine learning model which predicts the value of y when your independent variable is given. So whenever x is given, it will predict the value of y. So this is the machine learning model that you have built. Okay, after you found your value of beta naught and beta 1. Okay, we will do this. So once we start doing this in Python, once we'll do a lot of case studies on this, then it will become clear. I'm just getting the theory today first. Okay, once the theory is set, you will easily follow the hands-on part. Okay. So what else, guys? Any doubts? Anything you want to ask? So this is all that I wanted to cover for today. I did not. I don't want to move very fast and give you guys a lot to study per day. I want to take it really slow so that you absorb everything that I'm covering. Okay, because these things may be new to you, totally new to you. So I don't want to hurry up. So I want to go very slow. Arpita is asking RMSE disadvantage once more. Okay, so Arpita, the disadvantage of RMSE is that it gives you absolute, okay, absolute units. So let's say I'm trying to predict income of all my students. I'm trying to predict the income of all my students based on their age. Okay, and I have found out the RMSE value to be, let's say, 8,000. 8,000 rupees is the RMSE value. Now, if I ask you, is this a good model? Will you be able to tell me whether this is a good model or not? Will you be able to tell me whether this is a good model? You will not be able to tell me because you don't have any information. You don't have any information whether I am talking about monthly salary or I am talking about annual salary. So this error is on annual salary or is this on the monthly salary? You don't know. So you don't know the comparison, whether the actual income, whether it is 10 lakhs or whether it is, let's say, 30,000. If it is 10 lakhs, then 8,000 error is good. It's not bad. Because if actual value is 10 lakhs, your error is only 8,000. But if the actual value is 30,000 and the error is 8,000, then it's not a good model. Because even 30,000 it is not able to predict correctly. It is predicting with 8,000 error. But if it is 10 lakhs, then it is quite a good model. So you cannot say, basically, you need this number, you need this column to be able to make a conclusion that the model is good or not. So that is the disadvantage. But if you give it as a percentage, let's say 2%, then 2% means if it is 10 lakhs, you know how much it will be. If it is 2%, if it is 30,000, you know how much it will be. So that disadvantage is removed when you use mean absolute percentage error because of taking percentage. Okay, so that is the disadvantage of root mean squared error. Okay, anything else, guys? Anything else, or I'm done? This is all I had for today. So some of the students had mentioned they have office today, so they wanted me to go slow, and even without that I would have gone slow. This entire batch I'm going very slow. I don't want to hurry up in the batch, but please make use of this, guys. The whole so make this your strength that I'm going very slow. I can honestly tell you, whichever coaching center you go to, they will cover linear regression in one day. Even I do that when I teach for any training academy. I cover entire linear regression in one day. Okay, including the hands-on, the theory, everything. So if I am covering that slow for you guys, make use of this. Okay, how would you make use of this? Revise, make make yourself comfortable with the topic as soon as they are covered. Don't lag behind the class, stay with the class. Otherwise, what's the point of going slow if you are still lagging behind? The only disadvantage of taking joining any other coaching institute is that they go very fast, so you are not able to follow along with them. You lag behind, and if you lag behind, because every following class will require the knowledge of a previous class, and since you lag behind, it becomes difficult to follow. Okay, so if I'm going slow, make use of this. Stay with the class. I haven't covered a lot so far. You can easily catch up, and we have classes usually on the alternate weekends. Okay, so that means you get enough time to catch up. So work hard and catch up. Okay, so 8 to 15 hours is what I expected out of you. I told you initially very clearly that 8 to 15 hours every week you have to give. So please do that. Okay, and I have given you the learning portal also. Even institutes which charge the fees that I'm charging don't give such learning portal. I'm spending a lot of amount in taking this learning portal. This is not free. This learning portal I'm spending, and I have taken an annual package. I have spent almost 2 lakhs in the annual package. Okay, so please make use of this. I really want you guys to succeed. I'm not doing this just to make money. Okay. So the